Reading Practice, Multidisciplinary Engineering. Prepare by Hammad Al-Khayari. Chapter 1, Introduction to Multidisciplinary Engineering. 1.1 Overview of Multidisciplinary Engineering. Multidisciplinary engineering refers to the integration of knowledge and methodologies from various engineering disciplines to address complex problems that cannot be effectively solved by a single discipline alone. This approach fosters collaboration among engineers specializing in different fields such as mechanical, electrical, civil, chemical, and software engineering, among others. The primary goal is to leverage diverse perspectives and expertise to innovate and create comprehensive solutions that meet the multifaceted demands of modern engineering challenges. As technology evolves and societal needs become increasingly complex, the traditional boundaries between engineering disciplines are blurring. Multidisciplinary engineering is becoming essential in areas such as renewable energy systems, transportation networks, biomedical engineering, and smart cities, where solutions require a holistic understanding of various engineering principles and practices. 1.2 Importance of a multidisciplinary approach. The importance of a multidisciplinary approach in engineering cannot be overstated. Here are several key reasons why it is vital. 1. Complex problem solving. Many contemporary challenges, such as climate change, urbanization, and public health crises, require solutions that involve multiple engineering disciplines. A multidisciplinary approach facilitates comprehensive problem solving by integrating different methodologies and technologies. 2. Innovation and creativity. By combining insights from various fields, engineers can foster innovation and enhance creativity. Cross-pollination of ideas often leads to breakthrough technologies and novel solutions that would not emerge within the confines of a single discipline. Page 3. Collaboration and teamwork. Multidisciplinary engineering encourages collaboration among professionals with diverse skill sets. This teamwork enhances communication, understanding, and respect for different perspectives, ultimately leading to more robust and well-rounded engineering outcomes. 4. Adaptability to industry trends. The engineering landscape is constantly evolving with advancements in technology and shifts in societal needs. A multidisciplinary approach equips engineers with the versatility to adapt to these changes and effectively tackle emerging challenges. 5. Global impact. Many of the world's pressing issues, such as energy sustainability, infrastructure development, and healthcare accessibility, require collaborative efforts across disciplines. Multidisciplinary engineering empowers engineers to make a significant positive impact on society and the environment. 1.3 Structure of the PhD program. The PhD program in multidisciplinary engineering is designed to equip students with the skills and knowledge necessary to thrive in a collaborative engineering environment. The structure typically includes 1. Core coursework. Students take foundational courses in various engineering disciplines, including systems engineering, project management, and computational methods. This ensures a solid understanding of the principles across multiple fields. 2. Specialization. While the program emphasizes multidisciplinary collaboration, students are encouraged to select a specialization that aligns with their research interests, such as renewable energy, robotics, or biomedical applications. 3. Research component. A significant portion of the program is dedicated to research. Students work on interdisciplinary projects that address real-world problems, often in collaboration with industry partners or research institutions. Page 4. Collaborative projects. The program includes opportunities for students to participate in collaborative projects that involve teamwork with peers from different engineering backgrounds. This fosters practical experience in a multidisciplinary environment. 5. Dissertation. Students are required to complete a dissertation that demonstrates their ability to conduct independent research and contribute original knowledge to the field of multidisciplinary engineering. 6. Professional development. The program often includes workshops, seminars, and networking opportunities aimed at enhancing students' skills in communication, leadership, and project management. 1.4 Career opportunities in engineering. A PhD in multidisciplinary engineering opens up a wide array of career opportunities across various sectors. Graduates can pursue roles in 1. Research and development. Many PhD holders work in R&D departments within corporations, government agencies, or academic institutions, focusing on innovative engineering solutions. 2. Consulting. Engineers with multidisciplinary expertise often find roles in consulting firms, where they provide insights and solutions to complex engineering challenges for clients across different industries. 3. Project management. With their comprehensive understanding of various engineering disciplines, graduates are well suited for project management positions, overseeing multidisciplinary teams and ensuring project success. 4. Academia. Graduates may choose to enter academia, where they can teach and mentor future engineers while conducting research in their areas of expertise. 5. Industry leadership. Many PhD graduates move into leadership roles within organizations, driving strategic initiatives that require a multidisciplinary perspective. 3. Page 6. Entrepreneurship. Armed with advanced knowledge and innovative ideas, some graduates embark on entrepreneurial ventures, developing startups that address pressing societal issues through engineering solutions. In conclusion, the multidisciplinary engineering field is a dynamic and evolving discipline that offers significant opportunities for innovation and impact. Through a structured PhD program, aspiring engineers can prepare themselves to meet the challenges of today's complex world and contribute to a sustainable and technologically advanced future. Chapter 2, Aerospace Engineering 2.1 Fundamentals of Aerospace Engineering. Aerospace engineering is a specialized branch of engineering that focuses on the development of aircraft and spacecraft. This discipline encompasses a variety of principles from mechanical, electrical, and materials engineering, and applies them to the design, construction, and testing of vehicles that operate within Earth's atmosphere and beyond. The two main subfields of aerospace engineering are aeronautical engineering, which deals with aircraft, and astronautical engineering, which pertains to spacecraft. Key concepts in aerospace engineering include aerodynamics, the study of how air interacts with moving bodies. Understanding the forces of lift, drag, and thrust is crucial for designing efficient aircraft and spacecraft. Propulsion systems *. This encompasses the study of engines and propulsion methods, including jet engines, rocket engines, and alternative propulsion technologies. Structures and materials. Aerospace vehicles must be lightweight yet strong. This requires knowledge of advanced materials and structural analysis to ensure safety and performance under extreme conditions. 4-page, Control systems, the design of systems that control the flight of an aircraft or spacecraft, including navigation, stability, and guidance systems. Systems engineering, a holistic approach to designing aerospace systems, integrating various components, mechanical, electrical, software, to ensure they work together effectively. 2.2 Key areas of research. Research in aerospace engineering is continually evolving, driven by technological advancements and the demand for more efficient and safer air and space travel. Some key areas of research include sustainable aviation, investigating alternative fuels, hybrid electric propulsion systems, and noise reduction technologies to minimize the environmental impact of aviation. Autonomous systems, developing unmanned aerial vehicles, UAVs, and autonomous spacecraft that can operate without human intervention, utilizing advanced sensors and artificial intelligence. Hypersonic flight, exploring technologies that enable flight at speeds greater than Mach 5, which could revolutionize air travel and military applications. Space exploration technologies, researching reusable launch systems, in-situ resource utilization, and life support systems to support long-duration missions to the Moon, Mars, and beyond. Advanced materials, investigating composite materials, smart materials, and nanotechnology to improve the performance and durability of aerospace structures. 2.3 Integration with other engineering disciplines. 5-page Aerospace engineering is inherently interdisciplinary, requiring collaboration with various engineering fields to solve complex problems. Key integrations include mechanical engineering, the design of propulsion systems, control surfaces, and structural components relies heavily on mechanical engineering principles. Electrical engineering, Avionics systems, which include navigation, communication, and control systems, are vital for the operation of modern aircraft and spacecraft. Computer engineering, software development for flight control systems, simulations, and data analysis is critical in the design and operation of aerospace vehicles. Materials science, innovations in materials affect weight, performance, and safety. Aerospace engineers must work closely with materials scientists to select and develop appropriate materials. Systems engineering, effective project management and system integration are necessary for the successful delivery of aerospace projects, requiring knowledge from multiple engineering disciplines. 2.4 Case Studies in Aerospace Innovation 1. NASA's Space Shuttle program. The Space Shuttle was a significant achievement in aerospace engineering, demonstrating the ability to launch, orbit, and land reusable spacecraft. The program involved extensive collaboration across multiple engineering disciplines, leading to innovations in materials, propulsion, and robotics. 2 Boeing 787 Dreamliner. This aircraft exemplifies advancements in materials technology, utilizing composite materials to reduce weight and improve fuel efficiency. The integration of advanced avionics and systems engineering practices also highlights the importance of interdisciplinary collaboration in aerospace projects. 6 Page 3. SpaceX Falcon 9. The development of the Falcon 9 rocket has revolutionized access to space by introducing reusability in launch vehicles. SpaceX's innovative approach to engineering, rapid prototyping, and agile development has set new standards in the aerospace industry. For electric vertical takeoff and landing, eVTOL, aircraft, companies like Joby Aviation and Archer are pioneering the development of eVTOL aircraft for urban air mobility. These innovations aim to reduce congestion in urban areas and provide sustainable transportation solutions, showcasing the integration of aerodynamics, propulsion, and electrical engineering. 5 Mars rover missions. NASA's Mars rovers, such as Curiosity and Perseverance, highlight the integration of aerospace engineering with robotics and computer science. These missions require advanced systems engineering to develop autonomous vehicles capable of conducting scientific research on distant planets. Through these case studies, we can observe how aerospace engineering continually pushes the boundaries of technology, resulting in innovative solutions that influence various sectors beyond aerospace. Chapter 3, Biomedical Engineering 3.1 Introduction to Biomedical Engineering. Biomedical engineering is an interdisciplinary field that combines principles of engineering, biology, and medicine to develop technologies and systems that improve health care. This field aims to enhance the quality of life for patients by designing medical devices, developing imaging technologies, and creating biomaterials and prosthetics. Biomedical engineers work closely with healthcare professionals to understand the challenges faced in clinical settings and to innovate solutions that can lead to better diagnostic, therapeutic, and rehabilitation outcomes. The evolution of biomedical engineering has been driven by advances in technology and a deeper understanding of biological systems. With the integration of engineering principles in medical practice, this field has expanded to include various subdisciplines such as medical imaging, tissue engineering, and bioinformatics. As the population ages and healthcare demands increase, biomedical engineering is poised to play a critical role in addressing health challenges globally. 7 Page 3.2 Technologies in Healthcare. The integration of technology in healthcare has revolutionized patient care and medical practices. Some of the significant technologies in this domain include: 1. Medical imaging. Techniques such as MRI, CT scans, and ultrasound allow for non-invasive visualization of internal structures, aiding in accurate diagnosis and treatment planning. 2. Wearable health devices. Devices like smartwatches and fitness trackers monitor health metrics, example heart rate, activity levels, and facilitate remote patient monitoring, enabling proactive health management. 3. Robotic surgery. Surgical robots enhance precision and control during procedures, leading to minimally invasive operations and quicker recovery times. 4. Telemedicine. This technology allows healthcare providers to consult with patients remotely, improving access to care and reducing the need for in-person visits. 5. 3D printing, custom prosthetics, implants, and even biological tissues can be created using 3D printing technology, offering personalized solutions for patients. 6. Artificial intelligence, AI algorithms are increasingly used to analyze medical data, assist in diagnostics, and predict patient outcomes, enhancing decision-making in clinical environments. These technologies not only improve the efficiency of healthcare delivery but also empower patients to take an active role in managing their health. 8. Page 3.3 Ethical considerations in biomedical research. As biomedical engineering continues to progress, ethical considerations become paramount. Key ethical issues include: 1. Informed consent. Ensuring that patients and participants in research studies fully understand the procedures, risks, and benefits involved is essential for ethical practice. 2. Privacy and data security. With the rise of digital health technologies, protecting patient data from breaches and unauthorized access is critical. 3. Equity and access. Addressing disparities in access to biomedical innovations is vital to ensure that advancements benefit all segments of the population, not just those with resources. 4. Animal testing. The use of animals in research raises ethical questions about the treatment of living beings and the necessity of such studies for human health advancements. 5. Dual use of technology. Technologies developed for beneficial purposes can be misused for harmful applications. Ensuring that innovations are used ethically is a significant concern. 6. Regulatory compliance. Adhering to regulations and guidelines governing biomedical research ensures that projects are conducted responsibly and ethically. Navigating these ethical considerations is crucial for maintaining public trust and ensuring the responsible advancement of biomedical engineering. 3.4 Collaborative projects in biomedicine. 9-page collaboration across disciplines is essential for driving innovation in biomedical engineering. Successful collaborative projects often involve partnerships between engineers, medical professionals, researchers, and industry stakeholders. These collaborations can take various forms, including: 1. Interdisciplinary research teams, bringing together experts from various fields, such as biology, engineering, and computer science, to tackle complex health challenges and develop innovative solutions. 2. Public-private partnerships. Collaborations between government agencies and private companies can accelerate research and development of new technologies, ensuring that they reach the market efficiently. 3. Academic institutions and healthcare organizations. Joint initiatives between universities and hospitals can facilitate clinical trials, allowing for rapid testing and validation of new biomedical technologies. 4. Global health initiatives. Collaborative projects that address health issues on a global scale, such as infectious diseases, can leverage diverse expertise and resources to create impactful solutions. 5. Innovation hubs and incubators. Establishing environments that foster collaboration among startups, researchers, and healthcare professionals can lead to the rapid development of new technologies and therapies. Through collaboration, biomedical engineering can harness diverse perspectives and expertise, leading to breakthroughs that improve patient care and advance the field as a whole. Chapter 4, Chemical Engineering. 4.1 Basics of Chemical Engineering Processes. Chemical engineering is a multidisciplinary field that combines principles from chemistry, physics, biology, and mathematics to design, optimize, and operate processes that convert raw materials into valuable products. The fundamental processes in chemical engineering include 10 PAGE, unit operations. These are the basic steps in a chemical process, including operations like mixing, heat transfer, mass transfer, distillation, and chemical reactions. Each unit operation can be studied independently and is essential for the overall process design. Material balances. This principle involves accounting for all materials entering and leaving a system. It ensures that mass is conserved throughout the process, which is crucial for efficient design and operation. Energy balances. Similar to material balances, energy balances account for all energy entering and leaving a system. This is vital for understanding the thermodynamics of chemical processes and optimizing energy use. Reaction kinetics. Understanding the rates of chemical reactions allows engineers to design reactors that maximize production efficiency. Kinetic studies help in selecting appropriate reaction conditions and catalysts. Process control. This involves monitoring and controlling chemical processes to ensure they operate safely and efficiently. Control systems help maintain desired output levels and respond to disturbances in the process. 4.2 Role in sustainable development. Chemical engineering plays a pivotal role in sustainable development through green chemistry. Engineers are developing processes that minimize waste and reduce the use of hazardous substances. Green chemistry principles are integrated into chemical manufacturing to enhance environmental sustainability. Renewable energy. Chemical engineers are at the forefront of developing alternative energy sources, such as biofuels and solar energy technologies. They design efficient processes for converting biomass into energy and optimize energy storage systems. 11 PAGE, Waste management. Chemical engineering principles are applied to treat and recycle waste materials, transforming them into valuable resources. This includes designing processes for waste-to-energy conversion and developing biodegradable materials. Water treatment. Engineers design chemical processes for water purification and desalination, ensuring access to clean water, which is essential for health and development. Carbon capture and storage. The development of technologies to capture and store carbon dioxide emissions from industrial processes is crucial for mitigating climate change. Chemical engineers are involved in designing these systems. 4.3 Cross-disciplinary applications. Chemical engineering intersects with various fields, leading to innovative applications. Biotechnology. In bioprocessing, chemical engineers work with biologists to design processes for producing pharmaceuticals, enzymes, and biofuels through fermentation and other biological methods. Materials science. Chemical engineers collaborate with materials scientists to develop new materials with specific properties for applications in electronics, medicine, and construction. Environmental science. Engineers apply chemical principles to address environmental challenges, including pollution control, sustainable resource management, and ecosystem restoration. Nanotechnology. The manipulation of materials at the molecular level allows for the creation of nanoscale products. Chemical engineers are crucial in developing processes for synthesizing and scaling up nanomaterials. Food engineering. Chemical engineering principles are applied in food processing to improve safety, quality, and shelf life of food products while ensuring efficient production methods. 12 PAGE 4.4 Innovations in chemical engineering. The field of chemical engineering is continuously evolving, with several innovations shaping its future. Process intensification. This approach seeks to make chemical processes more efficient by reducing equipment size and energy consumption, often through the integration of multiple unit operations into a single step. Digitalization and AI. The use of artificial intelligence and machine learning is transforming process design and optimization. Advanced data analytics enable real-time monitoring and predictive maintenance of chemical plants. 3D printing. This technology is being explored for producing chemical reactors and other equipment, allowing for rapid prototyping and customization of chemical engineering systems. Smart materials. The development of responsive materials that can change properties in response to environmental stimuli holds promise for applications in various industries, including healthcare and electronics. Sustainable catalysis. Innovations in catalyst design and development are crucial for improving reaction efficiency and selectivity, leading to greener chemical processes. Through these innovations and applications, chemical engineering continues to play a vital role in addressing global challenges, driving technological advancement, and promoting sustainable practices. Chapter 5, Civil Infrastructure and Environmental Engineering. 5.1 Principles of Civil Engineering. 13 PAGE Civil engineering is a broad field that focuses on the design, construction, and maintenance of the built environment. The primary principles guiding civil engineering include: Key concepts. 1. Structural integrity. ensuring that structures can withstand loads and forces without failure. 2. Material selection, choosing appropriate materials based on strength, durability, cost, and environmental impact. 3. Geotechnical considerations, understanding the behavior of soil and rock to inform foundation design and stability. 4. Hydraulics and hydrology, managing water resources through the design of drainage systems, flood control, and water supply systems. 5. Transportation systems, designing roadways, bridges, and transit systems to facilitate safe and efficient movement of people and goods. Ethical and professional standards. Civil engineers must adhere to ethical standards, ensuring public safety, welfare, and environmental stewardship in their projects. This includes compliance with regulations, codes, and best practices. 5.2 Environmental Impact Assessment. Environmental Impact Assessment, EIA, is a critical process that evaluates the potential environmental effects of proposed projects before they are carried out. The key components of EIA include: Process Steps 1. Screening, determining whether a project requires a full EIA based on its potential impacts. 2. Scoping, identifying key issues and impacts that need to be assessed. 3. Impact analysis, evaluating the potential environmental impacts, including air and water quality, biodiversity, and socio-economic effects. 4. Mitigation measures, proposing strategies to avoid, reduce, or compensate for significant impacts. 5. Public participation, engaging stakeholders and the public to gather input and address concerns. 14. PAGE 6. Monitoring and compliance, establishing procedures to monitor impacts and ensure compliance with mitigation measures. Importance of EIA. EIA helps to promote sustainable development by ensuring that environmental considerations are integrated into decision-making processes, ultimately leading to better outcomes for communities and ecosystems. 5.3 Resilient infrastructure design. Resilient infrastructure design focuses on creating systems that can withstand and recover from adverse events such as natural disasters, climate change, and human-made disruptions. Key aspects include: Principles of resilience. 1. Robustness, designing infrastructure to endure extreme conditions without failure. 2. Redundancy, incorporating alternative systems or routes to ensure functionality in case of a failure. 3. Flexibility, allowing for adaptability in design to accommodate future changes and uncertainties. 4. Rapid recovery, ensuring that infrastructure can be quickly restored after a disruption. Strategies for resilience, climate adaptation, implementing design practices that consider future climate scenarios, such as increased rainfall or rising sea levels. Smart infrastructure, utilizing technology, example sensors and data analytics, to monitor conditions and improve decision-making. Community engagement, involving local communities in the planning process to ensure that infrastructure meets their needs and enhances their resilience. 5.4 Interdisciplinary sustainability practices. 15 PAGE Sustainability in civil infrastructure and environmental engineering requires collaboration across disciplines. Key practices include: collaborative approaches. 1. Integrated design, combining expertise from various fields, engineering, ecology, social sciences, to create holistic solutions. 2. Green infrastructure, implementing natural systems, example green roofs, permeable pavements, to manage stormwater and enhance urban ecosystems. 3. Life cycle assessment, evaluating the environmental impacts of a project throughout its entire life cycle, from material extraction to disposal. 4. Community-based approaches, engaging local populations in sustainability initiatives to ensure that projects are culturally and socially relevant. Education and training. Promoting interdisciplinary education and training for engineers, planners, and environmental scientists is essential for fostering a sustainable mindset and equipping professionals with the tools needed to address complex challenges. This chapter outlines the fundamental principles of civil engineering, the importance of environmental impact assessments, the need for resilient infrastructure design, and the value of interdisciplinary sustainability practices in creating a sustainable future. Chapter 6, Electrical and Computer Engineering 6.1 Foundations of Electrical Engineering 16 PAGE Electrical Engineering, EE, is a discipline that encompasses a broad range of topics related to electricity, electronics, and electromagnetism. The foundations of electrical engineering can be traced back to the late 19th century with pioneers like Thomas Edison and Nikola Tesla, whose innovations laid the groundwork for modern electrical systems. Key areas of study include circuit theory, understanding the fundamentals of electrical circuits, including Ohm's law, Kirchhoff's laws, and the analysis of AC and DC circuits. Electromagnetism, exploring the principles of electric and magnetic fields, Maxwell's equations, and their applications in communications and energy transfer. Signal processing, techniques for analyzing, manipulating, and interpreting signals, which are critical in communications, audio, and image processing. Control systems, the study of system dynamics and feedback mechanisms, enabling the design of systems that can operate automatically and efficiently. Power systems, focused on the generation, transmission, and distribution of electrical power, as well as the integration of renewable energy sources. 6.2 Advances in computing technologies. The field of computer engineering has seen tremendous advancements driven by rapid technological progress. Key areas of focus include microprocessors and microcontrollers, the development of smaller, more powerful chips that drive the performance of computers and embedded systems. Parallel and distributed computing, techniques that leverage multiple processors or computers to solve complex problems more efficiently, which is essential for applications like big data and cloud computing. Artificial intelligence and machine learning, the integration of AI into computing systems has transformed various fields, enabling smarter applications and automation. Quantum computing, an emerging area that promises to revolutionize computing by utilizing quantum bits, qubits, to perform complex calculations at unprecedented speeds. 17 PAGE, cybersecurity, as computing technologies advance, the need for robust security measures to protect data and systems has become paramount. 6.3 Integration with other engineering fields. Electrical and computer engineering does not exist in isolation, it increasingly intersects with various other engineering disciplines. This integration fosters innovation and enhances the capabilities of technology. Some notable integrations include mechanical engineering, the development of mechatronics, which combines mechanical systems with electronics and computing for applications like robotics and automation. Biomedical engineering, innovations in medical devices and health informatics rely heavily on electrical principles and computing technologies to improve healthcare delivery. Civil engineering, the use of smart grid technologies, sensors, and data analytics in infrastructure development and management. Chemical engineering, the integration of electrical engineering in process control and automation within chemical manufacturing. Environmental engineering, the application of electrical and computing technologies in monitoring and managing environmental systems, including renewable energy solutions. 6.4 Emerging trends and future directions. As the landscape of electrical and computer engineering continues to evolve, several emerging trends are shaping its future. Internet of Things, IoT. The proliferation of connected devices is driving the need for efficient communication protocols, data analytics, and security measures. Smart grids, advances in energy management systems aim to optimize electricity distribution and incorporate renewable energy sources more effectively. 18 PAGE, wearable technology, the rise of smart wearables is revolutionizing personal health monitoring and fitness industries, necessitating advancements in low-power electronics and communication. Autonomous systems, the development of self-driving vehicles and drones relies on sophisticated sensors, data processing, and control algorithms. Sustainability, with a growing emphasis on environmental responsibility, electrical and computer engineering is focusing on energy-efficient systems and sustainable practices. In conclusion, electrical and computer engineering is a dynamic and rapidly evolving field that plays a crucial role in shaping modern society. its foundations continue to be built upon while simultaneously integrating with other disciplines and embracing emerging technologies that promise to redefine the future. Chapter 7, Engineering Systems and Management 7.1 Systems Engineering Principles. Systems engineering is a multidisciplinary approach that focuses on the design, integration, and management of complex systems throughout their life cycles. Key principles include: holistic view, understanding that a system is more than the sum of its parts. It requires considering interactions and dependencies among components. Requirements definition, clearly defining and managing requirements is crucial for ensuring that the final system meets its intended purpose. Life cycle approach, systems should be considered from conception through development, operation, maintenance, and eventual disposal. Iterative development, employing iterative processes allows for feedback and continuous improvement throughout the system development life cycle. Stakeholder involvement, engaging stakeholders throughout the project ensures that the system meets user needs and expectations. Risk management, identifying, analyzing, and mitigating risks throughout the project is essential for successful system implementation. 19 PAGE 7.2 Project Management in Engineering. Project management in engineering encompasses planning, executing, and closing projects while adhering to specific constraints such as time, budget, and resources. Key components include: project planning, establishing a clear project scope, objectives, timeline, and resource allocation. Tools like Gantt charts and work breakdown structures are often used. Cost management, estimating, budgeting, and controlling costs to ensure that the project is completed within the approved budget. Quality management, ensuring that the project deliverables meet the required standards and specifications through quality assurance and control processes. Communication, maintaining effective communication among team members and stakeholders to facilitate collaboration and transparency. Risk management, identifying potential risks, analyzing their impact, and developing mitigation strategies to minimize their effects on the project. Performance monitoring, regularly tracking project progress against the plan and making necessary adjustments to stay on course. 7.3 Decision-making models. Effective decision-making is vital in engineering management. Various models guide the process. Rational decision-making model. This classical model involves defining the problem, identifying alternatives, evaluating options, and selecting the best course of action based on objective criteria. Bounded rationality model acknowledges that decision-makers operate under constraints of limited information and cognitive biases, leading to satisfactory rather than optimal solutions. Multi-criteria decision analysis, MCDA, a structured approach that evaluates multiple conflicting criteria in decision-making, often used in complex engineering projects. 20 PAGE, decision trees, visual representations of decisions and their possible consequences, including risks and rewards, aiding in the analysis of different options. Game theory, analyzes strategic interactions where the outcome depends on the choices of multiple decision-makers, useful in competitive engineering contexts. 7.4 Case studies in engineering management. Case studies provide insights into real-world application of engineering management principles. Examples include: Case Study 1, NASA's Mars rover mission. This project exemplifies systems engineering principles through its rigorous requirements definition, risk management strategies, and iterative testing phases. Case Study 2, Construction of the Burj Khalifa, highlights project management challenges in a large-scale engineering project, including resource allocation, cost management, and stakeholder engagement. Case Study 3, Development of Electric Vehicles, demonstrates decision-making models in the automotive industry, showcasing how manufacturers evaluate alternatives and navigate regulatory environments. Case Study 4, Disaster Recovery Engineering, examines how engineering systems can be designed for resilience, focusing on the lessons learned from recent natural disasters and the importance of rapid response planning. In summary, Chapter 7 emphasizes the importance of integrating systems engineering principles with effective project management and decision-making models to enhance the success of engineering projects. Through case studies, the application of these concepts in real-world scenarios illustrates their impact on engineering management practices. Chapter 8, Material Science and Engineering 8.1 Overview of Material Science. Material science is a multidisciplinary field that focuses on the study of materials and their properties, structures, and performance. It encompasses various categories of materials, including metals, ceramics, polymers, and composites. 21 PAGE The primary goal of material science is to understand how the atomic and molecular structure of materials influences their macroscopic properties and behavior. Key concepts in material science include structure-property relationships, understanding how the internal structure of materials affects their mechanical, electrical, thermal, and optical properties. Materials characterization. Techniques such as microscopy, spectroscopy, and diffraction are used to analyze the structure and properties of materials. Materials processing. Methods of shaping and forming materials, including casting, forging, and additive manufacturing. Performance and applications. Assessing how materials perform under different conditions and their suitability for specific applications in industries such as aerospace, automotive, electronics, and biomedical. 8.2 Nanotechnology and Advanced Materials. Nanotechnology involves the manipulation of materials at the nanoscale, typically between 1 and 100 nanometers. At this scale, materials exhibit unique properties that can differ significantly from their bulk counterparts. This chapter explores the implications of nanotechnology in developing advanced materials with enhanced functionalities. Key areas of focus include nanomaterials, such as nanoparticles, nanowires, and nanotubes, which offer superior strength, lighter weight, and enhanced electrical and thermal conductivity. Applications. Nanotechnology is transforming various industries, including drug delivery systems in medicine, lightweight composites in aerospace, and highly efficient photovoltaics in renewable energy. Challenges and risks. Addressing potential health and environmental concerns related to the production and use of nanomaterials, as well as regulatory issues. 8.3 Interdisciplinary applications. Material science intersects with various disciplines, leading to innovative applications that enhance technology and improve quality of life. This section discusses some of the interdisciplinary applications of material science. 22 PAGE, Biomedical Engineering, development of biomaterials for implants, drug delivery systems, and tissue engineering scaffolds designed to interact safely with biological systems. Electronics and photonics, advancements in semiconductor materials, flexible electronics, and photonic devices that improve performance and reduce power consumption. Energy storage and conversion, innovations in battery materials, fuel cells, and supercapacitors that enhance energy efficiency and storage capabilities. Environmental science, creation of materials for water purification, air filtration, and sustainable construction that address environmental challenges. 8.4 Future trends in materials research. The future of materials science and engineering is poised for significant advancements driven by ongoing research and technological innovations. This section examines emerging trends and their potential impacts. Sustainable materials, development of bio-based, recyclable, and environmentally friendly materials to reduce carbon footprints and promote sustainability. Smart materials, research into materials that respond dynamically to changes in their environment, such as shape memory alloys and self-healing polymers. Computational materials science, the use of algorithms and simulations to predict material properties and behaviors, significantly speeding up the design and discovery of new materials. Personalized materials, tailoring materials for specific applications and individual needs, particularly in fields like medicine and consumer products. In conclusion, material science and engineering are integral to the advancement of technology and innovation across various fields. As research continues to evolve, the potential for new materials to address global challenges and improve our daily lives remains vast and promising. 23 PAGE Chapter 9, Mechanical Engineering 9.1 Core Concepts in Mechanical Engineering. Mechanical engineering is a diverse and dynamic field that applies principles of physics, materials science, and mathematics to solve engineering problems. At its core, mechanical engineering encompasses several fundamental concepts: statics and dynamics. Statics deals with forces in equilibrium, while dynamics focuses on forces and motion. Understanding these principles is crucial for analyzing structures and mechanisms. Thermodynamics, this area studies the relationships between heat, work, and energy. Key laws of thermodynamics govern energy transfer and conversion processes, influencing everything from engines to refrigeration systems. Mechanics of materials, this involves studying how materials deform and fail under various types of stress and strain. Concepts such as tensile strength, fatigue, and fracture mechanics are essential for material selection and structural design. Kinematics and kinetics. Kinematics focuses on the motion of objects without considering forces, while kinetics involves the analysis of forces causing motion. These concepts are vital for designing moving systems, such as linkages and gears. Manufacturing processes. Understanding various manufacturing methods, including machining, welding, casting, and additive manufacturing, is essential for producing components efficiently and cost-effectively. 9.2 Applications in robotics and automation. Mechanical engineering plays a pivotal role in the development of robotics and automation technologies. Key applications include 24 PAGE, robotic manipulators. Mechanical engineers design robotic arms and manipulators that can perform tasks ranging from assembly to surgery. These systems often incorporate kinematic analysis to achieve precise movements. Autonomous vehicles. Mechanical engineering principles are applied in the design of autonomous vehicles, including their structural integrity, aerodynamics, and thermal management systems. Automation systems. Mechanical engineers work on designing automation systems that improve efficiency in manufacturing. This includes conveyor systems, robotic assembly lines, and automated quality control systems. Soft robotics, the development of soft robots, which use compliant materials to achieve flexibility and adaptability, represents an innovative area where mechanical engineering principles are applied to create robots that can safely interact with humans and delicate objects. 9.3 Thermal and fluid dynamics. Thermal and fluid dynamics are critical areas in mechanical engineering, impacting various applications and systems. Heat transfer. Understanding conduction, convection, and radiation is essential for designing systems that efficiently manage heat, such as heat exchangers and thermal insulation. Fluid mechanics. This field studies the behavior of fluids, liquids and gases, in motion and at rest. Key concepts include fluid flow, pressure, and viscosity, which are crucial for designing pumps, turbines, and HVAC systems. Computational fluid dynamics, CFD. CFD uses numerical methods to analyze fluid flow and heat transfer. Engineers use CFD simulations to optimize designs in aerospace, automotive, and energy sectors. Thermal systems design. Mechanical engineers design thermal systems such as engines, refrigerators, and power plants, ensuring they operate efficiently while adhering to environmental regulations. 25 PAGE 9.4 Innovation in mechanical design. Innovation is at the heart of mechanical engineering, driving advancements across industries. Key trends include sustainable design. Engineers are increasingly focused on creating products and systems that minimize environmental impact. This includes using renewable materials, optimizing energy efficiency, and implementing life cycle assessment practices. Additive manufacturing, also known as 3D printing, this technology allows for the rapid prototyping and production of complex geometries that were previously impossible to manufacture with traditional methods. Smart materials, the development of materials that respond to environmental changes, such as temperature, pressure, or electric fields, opens new possibilities for innovative designs in fields like aerospace, robotics, and biomedical engineering. Digital twin technology. This involves creating a virtual model of a physical system to simulate performance and optimize operations. Engineers can use digital twins to predict failures, reduce downtime, and enhance maintenance strategies. Collaborative engineering, advances in software and communication technologies facilitate collaborative design processes, enabling teams to work together more effectively across geographical boundaries and disciplines. In summary, mechanical engineering is a multifaceted discipline that combines core principles with innovative applications in various fields, driving technological advancements and improving our quality of life. Chapter 10, Nuclear Engineering 10.1 Principles of Nuclear Engineering 26 PAGE Nuclear engineering is a field that focuses on the processes, systems, and technologies related to the production and utilization of nuclear energy. It encompasses the study of nuclear reactions, radiation, and the interactions of nuclear materials. The fundamental principles include nuclear reactions. Understanding fission, fusion, and radioactive decay is crucial. Fission, the splitting of heavy atomic nuclei, is the primary reaction used in nuclear reactors, while fusion, the combining of light nuclei, holds potential for future energy production. Radiation physics, this involves the study of different types of radiation, alpha, beta, gamma, and their properties, interactions with matter, and detection methods. Thermodynamics and fluid mechanics, these principles are essential for designing and analyzing nuclear reactors and their cooling systems, ensuring efficient heat transfer and reactor safety. Materials science, nuclear engineers must understand how materials behave under radiation and high temperatures, which is critical for reactor core design and fuel cycle management. 10.2 Safety and regulatory issues. Safety and regulatory concerns are paramount in nuclear engineering due to the potential hazards associated with nuclear materials and radiation exposure. Key aspects include regulatory frameworks. Various international and national bodies, such as the International Atomic Energy Agency, IAEA, and the U.S. Nuclear Regulatory Commission, NRC, set safety standards and regulations for nuclear facilities. Safety culture. Promoting a strong safety culture within organizations is essential for preventing accidents and ensuring compliance with regulations. This involves training, transparency, and commitment to safety at all levels. 27 PAGE, Accident Prevention and Mitigation. Engineers design reactors with multiple safety systems to prevent accidents. In the event of a failure, emergency response plans are crucial to minimize risks to public health and the environment. Waste management. The safe handling, storage, and disposal of nuclear waste are critical challenges. Engineers work on solutions for long-term waste management, including geological disposal methods. 10.3 Applications in energy production. Nuclear energy is a significant source of electricity worldwide, offering benefits such as low greenhouse gas emissions and high energy density. Key applications include nuclear power plants. These facilities use nuclear fission to generate steam, which drives turbines to produce electricity. Modern reactors are designed for efficiency and safety. Small modular reactors, SMRs. SMRs are emerging as a flexible and scalable option for energy production, offering advantages in safety and reduced construction times. Research reactors. These are used for scientific research, training, and the production of isotopes for medical and industrial applications. Nuclear heating and desalination. Nuclear energy can also be used for district heating and desalination processes, showcasing its versatility beyond electricity generation. 10.4 Interdisciplinary research in nuclear technologies. Nuclear engineering intersects with various fields, fostering innovative solutions and advancements. Key areas of interdisciplinary research include 28 PAGE, medical applications. The development of radiopharmaceuticals for cancer treatment and diagnostic imaging relies on nuclear technology and engineering principles. Nuclear fusion research. Efforts to harness fusion as a clean energy source involve collaboration with physicists, materials scientists, and engineers to develop viable reactor concepts. Environmental science. research on the environmental impacts of nuclear energy, including emissions and waste management, requires collaboration with environmental scientists and policymakers. Cybersecurity: as nuclear facilities become more reliant on digital systems, interdisciplinary approaches are needed to enhance cybersecurity measures and protect critical infrastructure. In summary, nuclear engineering encompasses a broad range of principles, safety considerations, applications, and interdisciplinary research areas. As the demand for sustainable energy solutions grows, the role of nuclear engineering will continue to evolve, offering innovative approaches to meet global energy needs. Chapter 11, Petroleum Engineering 11.1 Overview of Petroleum Engineering. Petroleum engineering is a specialized field that focuses on the extraction and production of hydrocarbons, primarily crude oil and natural gas. This discipline integrates principles from various engineering fields, including mechanical, civil, chemical, and geological engineering. Petroleum engineers are responsible for designing and implementing methods for extracting oil and gas from reservoirs, optimizing production processes, and ensuring the safe and efficient operation of drilling and extraction equipment. Key responsibilities within petroleum engineering include reservoir engineering, analyzing reservoir behavior and developing strategies to enhance oil recovery. 29 PAGE, drilling engineering, designing drilling plans and selecting appropriate technologies for drilling wells. Production engineering, managing the production phase to maximize efficiency and safety. Completion engineering, planning and executing the final stages of well construction to ensure optimal flow of hydrocarbons. The petroleum industry plays a crucial role in the global economy, supplying energy, fueling transportation, and providing raw materials for countless products. 11.2 Exploration and Production Techniques. Exploration and production of petroleum involve several key techniques and technologies that help locate and extract hydrocarbons. Exploration techniques. 1. Seismic surveys, utilizing sound waves to create images of subsurface structures, helping to identify potential oil and gas reserves. 2. Geological mapping, studying rock formations and geological structures to locate potential reservoirs. 3. Exploratory drilling, drilling wells in promising locations to confirm the presence of hydrocarbons. Production techniques. 1. Primary recovery, using natural reservoir pressure and pumping to extract oil and gas. Typically, this method recovers about 10 to 20% of the total hydrocarbons. 2. Secondary recovery, injecting water or gas into the reservoir to maintain pressure and enhance recovery, potentially increasing extraction to 30 to 50%. 3. Tertiary recovery, enhanced oil recovery, EOR, implementing advanced techniques such as thermal recovery, gas injection, and chemical flooding to further increase recovery rates, sometimes exceeding 60%. Offshore versus onshore production. Onshore production involves drilling wells on land and is generally less costly and logistically simpler. 30 PAGE, offshore production, requires specialized platforms and technology for deep water drilling and is often more expensive but can access larger reserves. 11.3 Environmental considerations. The petroleum industry faces significant environmental challenges and scrutiny. Key environmental considerations include 1. Pollution, oil spills, gas flaring, and emissions from drilling and production processes can harm ecosystems and communities. 2. Water usage, large quantities of water are often required for hydraulic fracturing and other production techniques, raising concerns about water scarcity and contamination. 3. Land disturbance, drilling activities can disrupt local wildlife habitats and landscapes. 4. Greenhouse gas emissions, the extraction and combustion of fossil fuels contribute significantly to climate change. To mitigate these impacts, the industry is increasingly adopting sustainable practices, such as implementing stricter regulations and monitoring systems, utilizing advanced technologies to minimize emissions and waste, investing in renewable energy sources and carbon capture and storage (CCS) technologies. 11.4 Future of energy resources. The future of energy resources is influenced by various factors, including technological advancements, environmental policies, and global energy demands. Transition to renewable energy. The shift towards renewable energy sources, such as solar, wind, and biofuels, is gaining momentum as countries strive to reduce greenhouse gas emissions and combat climate change. Petroleum engineers are exploring ways to integrate renewable technologies with traditional oil and gas operations, such as offshore wind farms and geothermal energy. 31 PAGE Innovations in petroleum engineering. The development of digital technologies, such as artificial intelligence and data analytics, is enhancing exploration and production efficiency. Advanced materials and drilling techniques are being researched to reduce costs and environmental impacts. Global energy dynamics. The demand for energy is expected to rise, particularly in developing nations, leading to ongoing exploration and production of hydrocarbons. Geopolitical factors and market fluctuations will continue to shape the oil and gas industry, requiring adaptability from petroleum engineers. Sustainable practices. The industry is increasingly focusing on sustainability, emphasizing the importance of responsible resource management and corporate social responsibility. Collaborations between governments, companies, and communities are essential for developing sustainable energy solutions. In conclusion, while the petroleum industry faces significant challenges, it also has the potential to innovate and adapt, ensuring a balanced approach to meeting global energy needs in the future. Chapter 12, Robotics. 12.1 Fundamentals of Robotics Engineering. Robotics engineering combines principles from mechanical engineering, electrical engineering, computer science, and control systems to design, build, and operate robots. Key components of robotics include 32 PAGE, kinematics, the study of motion without considering forces. It involves analyzing the position, velocity, and acceleration of robots, often using mathematical models to describe motion paths. Dynamics. This involves evaluating the forces and torques that cause motion. It is crucial for understanding how robots interact with their environments. Control systems. These systems regulate the behavior of robots. They can be open loop, no feedback, or closed loop, with feedback, and commonly utilize algorithms for stabilization and trajectory tracking. Sensors and actuators. Sensors provide data about the robot's environment, example cameras, LiDAR, while actuators are responsible for movement, example motors, hydraulic systems. Programming and AI. Robots require software to interpret sensory data, make decisions, and perform tasks autonomously. This often involves artificial intelligence and machine learning techniques. 12.2 Robotics in industry and medicine. Robotics plays a transformative role in various sectors. Industrial robotics. In manufacturing, robots are used for tasks like welding, painting, assembly, and packaging. They increase efficiency, precision, and safety while reducing labor costs. Medical robotics. Surgical robots enhance precision in operations, allowing for minimally invasive procedures. Robots are also employed in rehabilitation, diagnostics, and patient care, improving outcomes and reducing recovery times. Logistics and warehousing. Robots automate inventory management, sorting, and transportation, streamlining supply chains and reducing operational costs. Agricultural robotics. Robots assist in planting, harvesting, and monitoring crops, contributing to increased agricultural productivity and sustainability. 12.3 Interdisciplinary approaches to robotics. Robotics is inherently interdisciplinary, integrating knowledge from various fields. Cognitive science. Understanding human cognition aids in developing robots that can learn and adapt in complex environments. 33 PAGE, biomechanics. Insights from human and animal movement inform the design of robotic limbs and mobility systems. Human-robot interaction. HRI research in HRI focuses on building robots that can effectively communicate and collaborate with humans, ensuring safety and usability. Ethics and policy. As robots become more integrated into society, ethical considerations regarding their use, impact on employment, and decision-making processes become increasingly important. 12.4 Future Trends in Robotics Technology. The field of robotics is rapidly evolving, with several trends shaping its future. Advancements in AI and machine learning. Enhanced algorithms will allow robots to learn from their environments, enabling more advanced autonomy and decision-making. Collaborative robots, cobots designed to work alongside humans. Cobots will become more prevalent in workplaces, focusing on safety and ease of use. Swarm robotics, utilizing principles from nature. Swarm robotics involves multiple robots working together to accomplish tasks efficiently, such as search and rescue operations. Soft robotics, employing flexible materials. Soft robotics aims to create robots capable of safe interactions with humans and delicate objects, expanding their applications in various fields. Integration of IoT, the Internet of Things, IoT, will enhance robotic capabilities through improved connectivity, data sharing, and real-time monitoring, leading to smarter and more responsive systems. Sustainability, future robotics will increasingly focus on eco-friendly designs and applications that minimize environmental impact, contributing to sustainable development goals. As robotics continues to advance, its applications will expand, offering innovative solutions to complex challenges across multiple domains. Chapter 13, Research Methodologies in Multidisciplinary Engineering. 34 PAGE. This chapter explores various research methodologies pertinent to multidisciplinary engineering, emphasizing the integration of qualitative and quantitative methods, experimental design, interdisciplinary collaboration, and effective communication of research findings. 13.1 Qualitative and Quantitative Research Methods. Qualitative research methods. Qualitative research is primarily exploratory and aims to understand underlying reasons, opinions, and motivations. In multidisciplinary engineering, qualitative methods can be particularly useful for case studies, analyzing specific instances or projects to draw insights about processes and outcomes. Interviews and focus groups, gathering in-depth perspectives from stakeholders, including engineers, designers, and end users. Ethnographic studies, observing and interpreting the behaviors and interactions within engineering teams or user environments. Quantitative research methods. Quantitative research involves the systematic empirical investigation of phenomena via statistical, mathematical, or computational techniques. Key components include surveys and questionnaires, collecting numerical data from a large sample to identify trends and patterns. Statistical analysis, employing statistical tests to analyze data, such as regression analysis, ANOVA, and hypothesis testing. Modeling and simulations, using mathematical models to predict outcomes and test scenarios in engineering applications. Integration of methods. 35 PAGE. In multidisciplinary engineering, combining qualitative and quantitative methods, mixed methods, enhances research robustness. For instance, qualitative insights can inform the design of quantitative surveys, and quantitative results can validate qualitative findings. 13.2 Experimental Design and Analysis. Principles of experimental design. Experimental design is critical for conducting research that yields valid and reliable results. Key principles include control, maintaining consistency across experimental conditions to isolate the effects of the independent variable, S. Randomization, randomly assigning subjects or conditions to mitigate bias and ensure representativeness. Replication, repeating experiments to confirm findings and enhance the reliability of results. Types of experimental designs. Common experimental designs in multidisciplinary engineering include factorial designs, exploring the effects of multiple factors simultaneously. Randomized controlled trials, RCTs, comparing outcomes between a treatment group and a control group. Longitudinal studies, observing subjects over an extended period to assess changes and causative relationships. Data analysis techniques. Effective data analysis is crucial for interpreting experimental results. Techniques may include descriptive statistics, summarizing data through means, medians, modes, and standard deviations. Inferential statistics, drawing conclusions about populations based on sample data, using confidence intervals and hypothesis testing. 36 PAGE, analysis of variance, ANOVA comparing means among multiple groups to determine if significant differences exist. 13.3 Interdisciplinary collaboration techniques. Importance of collaboration. Interdisciplinary collaboration is essential in multidisciplinary engineering, as it fosters innovation and comprehensive problem-solving by integrating diverse expertise. Techniques for effective collaboration, cross-disciplinary workshops, organizing meetings that bring together professionals from different fields to brainstorm and share insights. Collaborative tools, utilizing digital platforms, example Slack, Microsoft Teams, to facilitate communication and project management across disciplines. Shared goals and objectives, establishing common objectives that align with the interests of all disciplines involved to ensure commitment and engagement. Managing team dynamics. Effective collaboration requires strong team dynamics. Strategies include role definition, clearly defining roles and responsibilities to avoid overlap and confusion. Conflict resolution, implementing strategies to address and resolve conflicts constructively. Regular check-ins, scheduling periodic meetings to assess progress, address challenges, and reinforce collaboration. 13.4 Writing and presenting research findings. Writing research findings. 37 PAGE Communicating research findings effectively is crucial for sharing knowledge and impacting practice. Key elements include structure, organizing research papers into clear sections, introduction, methodology, results, discussion, conclusion. Clarity and precision, using clear and precise language to convey complex concepts, avoiding jargon where possible. Visual aids, incorporating graphs, tables, and charts to enhance understanding and illustrate key points. Presenting research findings. Effective presentation of research findings can influence stakeholders and promote acceptance of new ideas. Considerations include audience awareness, tailoring presentations to the knowledge level and interests of the audience. Engaging delivery, using storytelling techniques, visuals, and interactive elements to engage the audience. Feedback mechanisms, encouraging questions and discussions to clarify points and gather diverse perspectives. Conclusion. Understanding and employing appropriate research methodologies in multidisciplinary engineering is essential for innovation and problem solving. By integrating qualitative and quantitative approaches, designing robust experiments, fostering interdisciplinary collaboration, and effectively communicating findings, researchers can contribute significantly to the advancement of engineering knowledge and practice. Chapter 14, Dissertation Development and Defense. 14.1 Choosing a research topic. 38 PAGE Choosing a research topic is a critical first step in your dissertation journey. It sets the foundation for your entire research project and can significantly influence your academic and professional trajectory. Here are some key considerations for selecting a compelling and feasible topic. 1. Personal interests and passion. Identify areas within your field that excite you. Consider what questions or problems you find intriguing and worth exploring. 2. Literature review. Conduct a thorough review of existing literature to identify gaps in knowledge. Look for areas that need further exploration or where you can contribute new insights. 3. Feasibility. Assess the availability of resources, data, and access to necessary populations or materials. Determine if the scope of the research is manageable within your time frame and resources. 4. Relevance and impact. Choose a topic that addresses current issues or challenges in your field. Consider the potential implications of your research for practitioners, policymakers, or academia. 5. Consultation. Seek advice from your advisor, faculty members, and peers. Engage in discussions to refine your ideas and receive constructive feedback. 39 PAGE 14.2 Structuring the dissertation. A well-structured dissertation is essential for effectively communicating your research findings. While specific formats may vary by discipline, A typical dissertation structure includes the following components: 1. Introduction. Introduce the research topic, its significance, and your research questions or hypotheses. Outline the structure of the dissertation. 2. Literature review. Provide a comprehensive overview of relevant literature, highlighting key theories, concepts, and previous research. Identify gaps that your research aims to fill. 3. Methodology. Describe the research design, including data collection and analysis methods. Justify your chosen methods and discuss any ethical considerations. 4. Results. Present the findings of your research clearly and systematically. Use tables, figures, and charts to enhance clarity. 5. Discussion. Interpret the results in the context of the research questions and existing literature. Discuss the implications of your findings, limitations of the study, and suggestions for future research. 40 #14.3 Preparing for the defense. The dissertation defense is a pivotal moment in your academic journey. Proper preparation can help you present your work confidently and effectively. Here are some strategies to prepare. #1. Understand the format. Familiarize yourself with the format and expectations of your defense, including the duration and the types of questions you may encounter. #2. Practice your presentation. Create a clear and concise presentation summarizing your research. Rehearse multiple times, ideally in front of peers or mentors who can provide constructive feedback. #3. Anticipate questions. Prepare for potential questions from your committee members by considering areas of your research that may raise discussion or critique. Think about the strengths and weaknesses of your research and how to address them. #4. Engage with your committee. Familiarize yourself with your committee members' research interests and previous work. Be ready to discuss how your work relates to their expertise. #5. Stay calm and confident. Practice relaxation techniques to manage anxiety. 41 PAGE. Remember that you are the expert on your research, and your committee is there to support you. 14.4 Post-PhD Career Pathways. After completing your PhD, several career pathways may open up. It's essential to consider your interests, skills, and the job market. Here are some common options. 1. Academia. Pursue a career in teaching and research at colleges or universities. Consider postdoctoral positions to further develop your research profile. 2. Industry. Explore opportunities in private sector companies, particularly those related to your field of study. Roles may focus on research and development, consulting, or management. 3. Government and nonprofit organizations. Work in policy analysis, research, or program management for government agencies or nonprofit organizations. Engage in projects that apply your research skills to address social issues. 4. Entrepreneurship. Start your own business or consultancy based on your research expertise. Innovate solutions or products that meet identified needs. 5. Freelancing and contract work. 42 PAGE. Offer your expertise as a freelancer, providing research, writing, or consulting services. 6. Further training or certification. Consider additional training or certifications to broaden your skill set or pivot to a new field. In conclusion, the transition from PhD student to a professional in your chosen field is a significant step. By effectively navigating the dissertation process and exploring career options, you can position yourself for success in your post-PhD endeavors. Chapter 15, Conclusion. 15.1 Summary of key learnings. In this chapter, we reflect on the essential insights gained throughout our exploration of multidisciplinary engineering. The integration of various engineering disciplines has proven to be crucial in addressing complex challenges in today's world. We have learned that collaboration is key. Effective multidisciplinary teams leverage diverse expertise, fostering innovative solutions that a single discipline cannot achieve alone. Systems thinking. Understanding the interconnections between components in a system is vital for creating efficient and sustainable designs. This holistic approach enhances problem-solving capabilities, adaptability and lifelong learning. As technology and industry demands evolve, engineers must be willing to continuously update their skills and knowledge across various fields. Ethics and responsibility. Engineers have a profound impact on society and the environment, thus, ethical considerations must be integrated into every stage of the engineering process. Global perspective. The challenges faced by engineers are often global in nature, requiring a collaborative approach that transcends geographical boundaries and cultural differences. 43 PAGE. These key learnings underscore the importance of fostering a multidisciplinary mindset in engineering education and practice. 15.2 The future of multidisciplinary engineering. Looking ahead, the future of multidisciplinary engineering is bright and full of opportunities. The rapid pace of technological advancement and the increasing complexity of global challenges, such as climate change, urbanization, and public health, necessitate a more integrated approach to engineering. Key trends shaping this future include increased integration of technology. Emerging technologies, such as artificial intelligence, machine learning, and the Internet of Things, will enhance the capabilities of multidisciplinary teams in analyzing data and optimizing designs. Sustainability as a core principle. The push for sustainable engineering practices will drive collaboration among disciplines to develop solutions that minimize environmental impact while meeting societal needs. Interdisciplinary education. Educational institutions are increasingly adopting interdisciplinary curricula that prepare students to work in diverse teams and tackle complex problems from multiple angles. Global collaboration. The interconnected nature of today's challenges will foster partnerships across borders, leading to innovative solutions that leverage diverse perspectives. As we embrace these trends, it is clear that multidisciplinary engineering will play a pivotal role in shaping a sustainable and technologically advanced future. 15.3 Encouragement for aspiring engineers. To aspiring engineers, we encourage you to embrace the principles of multidisciplinary engineering. Here are a few key pieces of advice. 1. Explore beyond your discipline. Engage with fields outside your primary area of study. Attend workshops, seminars, and interdisciplinary projects to broaden your horizons and discover new interests. 44 PAGE2. Cultivate collaboration skills. Build strong communication and teamwork skills, as these are essential for working effectively in diverse teams. Practice active listening and openness to different viewpoints. 3. Stay curious and adaptive. Embrace a mindset of lifelong learning. Stay updated with emerging technologies and industry trends, and be willing to adapt to new challenges. 4. Think ethically. Always consider the societal and environmental impacts of your work. Strive to design solutions that are not only innovative but also responsible and sustainable. 5. Network and connect. Build relationships with peers, mentors, and professionals in various fields. Networking can open doors to collaborative opportunities and enrich your understanding of multidisciplinary approaches. By fostering these qualities, you can position yourself as a valuable contributor to the exciting future of multidisciplinary engineering. The challenges ahead are complex, but with creativity, collaboration, and a commitment to continuous growth, you can help shape a better world through engineering. Index A, Appendices, 1. A.1 Resources for multidisciplinary engineering research, 2. A.2 Professional organizations and societies, 3. A.3 Funding opportunities for PhD students, 4. A.4 Networking and collaboration platforms, 5. C45 PAGE, Collaboration platforms, 5. Conference proceedings, 6. Cross-disciplinary research, 7. Data analysis techniques, 8. Design thinking in engineering, 9. Doctoral programs, 10. Engineering disciplines overview, 11. Emerging technologies, 12. Funding opportunities, 4. Grants, 13. Scholarships, 14. Glossary, 15. Index, 16. Networking strategies, 1746 PAGE, Networking and collaboration platforms, 5p, professional development, 18, professional organizations, 3r, references, 19, research methodologies, 20s, sustainability in engineering, 21, system integration, 22t, technology transfer, 23, transdisciplinary approaches, 24. This index reflects the structure of the book, making it easier for readers to navigate through topics relevant to their multidisciplinary PhD in engineering journey. Each entry is designed to guide users to specific sections that might interest them, facilitating research and exploration in the interconnected fields of engineering. 47 PAGE